we stopped the last lecture by saying, okay, we defined what a Hopf algebra is, rather bi-algebra, let's still go into distinction. And while I gave you one example of Hopf algebra, so I take words, the equivalent is the shuffle product, you take this co-product deconcatenation, and you can actually check it that satisfies all the axioms of Hopf algebra. The one thing I should have said is that delta is linear. So whenever you have delta acting on, say, a rational number, all you do is vector spaces over Q, and delta is linear. So whenever you have a rational number, it goes out to delta. Okay? All the maps that I write down are always linear with respect to rational numbers. Okay. And so from this you see, well, every shuffle algebra is naturally a Hopf algebra. And so I guess it's very clear that you can now, well, it's very natural to say, okay, then probably also polars are Hopf algebras. So that goes back to Goncharov in its first incarnation. Then we extended that. This was around 98. And then more recently, Francis Braun around 2013, 2012, around that. So, I want to define a co-product on polygons now, on multiple polygons. I will not give you the formula for the co-product on the most multiple polygon, because that would take probably more than an hour just to define all the things rigorously. So I just define it for the simplest incarnations, which is the logarithm and the classical polygons, E2, E3, E4. They're the formulas in Eisenhower, I can just write them down. All these formulas exist in the most general case, but they get rather technically involved and very subtle if you really look at the details. So, well, let's try to guess what the co-product of the logarithm could be. What could this possibly be? Well, if you compare it with the thing up there, I guess the most natural thing you can write down is this. What? Because letters are objects of weight 1, etc. Those are the simplest objects that you have. So that's what you would expect the co-product of the logarithm to be, and indeed that is the case. That is what you also naively expect. I mean, the logarithm is, yes, it's a transcendental function, but it's kind of the building block from which all other polygons are built, so there's no reason why it should be able to break that into anything simple in itself. Then, you said, what about, for example, Ln? Ln is as follows. So there's always a term, these two terms, 1 tends to the function plus the function tends to 1. They're always there. Okay. It's like a trivial statement that if you take any objects, there are always two trivial ways to breaking it apart, which is not to break them apart at all. But now, if I'm at higher weights, there's another bunch of terms. And they look like this. So maybe let's just write this out explicitly for n equals 2. Delta v2 of x equals 1 tensor v2 of x plus v2 of x tensor 1 minus this first item as plus e1 of x tensor log of x. Here there's only the term k equals 1, so I get log to the power 1 divided by 1. Li 2 minus 1, 1. And I remind you that Li1 is actually minus log 1 minus x. Okay? Now that looks innocent. That's the definition. The non-trivial part is, of course, that you now have to go and check that all the axioms are satisfied. In particular, there are generalizations of these formulas to multiple polylogs. You still have to check that all the axioms are satisfied. And if you're really rigorous, then it's even more complicated than that. So let's go there. So for now, take that as definition. And indeed, all axioms you can show, it was done with launch of the all axioms are satisfied, you get a whole function. Okay. Good. Now, what does this imply? Well, one thing that we said this morning is that Ln, evaluated as 1, is zeta n. Right, the Riemann zeta function. Because n here is bigger than 1, otherwise I would assume. Okay, so in particular that tells me that I can also now compute delta of zeta n. Right? Because I know that zeta n is Li of 1. And Li of 1, I use this formula, so I get 1 tensor Li of 1, which is zeta n, plus zeta n tensor 1, plus, well, here you have log of 1, so all these terms are actually 0. So, you find that the coproduct of zeta n and great integer greater 1 has this minus in complex form. Okay, it's very beautiful. But, well, those of you who know where the story is going, with this now you have a problem. Why do you have a problem? So, I guess you know that zeta 3, zeta 2 is actually pi squared over 6, right? Zeta 4 is pi 4 over 90, which is 2 divided by 5 zeta 2 squared. Okay? In general, zeta 2n is proportional to pi to the power 2n. This was shown by Euler already a few hundred years ago. Okay? That's very nice, because you see, we can now go and compute zeta 4 as 2 divided by 5 zeta 2 squared. Well, it's linear, delta is linear as said, so it's second rational number, so I get this. And pull that guy out. And since delta preserves the multiplication, I can also pull out the square. And I get 2 divided by 5. Well, I use that formula with 1 tensor zeta 2 plus zeta 2 tensor 1 square. And if you now go and you multiply everything out, you get zeta 4 plus zeta 4 tensor 1 plus 4 divided by 5 zeta 2 times of zeta 2. And that, I guess you can see the problem. Okay? I've arrived at the contradiction. I've computed delta zeta 4 in 2 ways and I get 2 different answers.
But I mean, it depends on the definition I give of the coproduct, right?
What?
I mean, if
No, I mean, it's not that I have this. I put x equals 1, I get that. I also know that zeta 4 is that. I haven't done nothing. I just know that zeta 4 has that property, and delta has that property that concludes me to get to that. I've used the same delta. I've started from here. That tells me zeta 4 is that. And I've used the same delta, which has certain properties, to derive from that.
How do you know that the delta square is not?
Can you speed up?
Yeah. How do you know that the delta of the square matches the square delta effect?
Because before the break, we said that you must have this. Right? So also for squares it holds. And tensors multiply component-wise, and if you go through the algebra, that's what you find. So in the process of saying that I have a Hopf algebra, all of these calculation rules are built in. I say that must hold. Otherwise I don't get a Hopf algebra in the first place. Okay? Yeah, more questions? This is a very important point. So, how can you solve this issue? There's one way you can solve it, which you're going to say now it's probably going to make you laugh, but it's not funny. Of course, if that was the case, then of course I would get 0 to 0 everywhere. That is indeed the solution by Goncharov. Goncharov was not an idiot, okay? It means that you have to mod out by something. It means you work modulo something. Which morally you can always say is like putting something to 0. The other way, back to Barton, it's very recent, it's like, less than 10 years ago, is to say zeta 2n, because it holds for zeta 2, it holds for zeta 2n in general, okay? So there's something special about the even zetas. Only half of them is there. You can easily check if that is the case, then all the terms that have zeta 2 in the second slot are not there and the problem goes away. This may look stupid and innocent, but it's very deep. Because actually what you're doing is since zeta 2n is just cos of pi, it actually comes from here. And what is 2 pi I? 2 pi I is precisely the thing that characterizes the discontinuities of something in this world. So the statement is actually that in all but the first slot, you have to work modulo discontinuities. And working modulo discontinuities is the same as working modulo I pi, because every discontinuity will be proportional to 2 pi I, to a residue. Okay? So, when you see this, the meaning of that, if you want, is it's modulo discontinuities, except for the first entry. And Goncharhov's way was modulo discontinuities everywhere. Yeah, so then that makes it a bit clearer. It's not that there's something magical happening here and just putting a number to 0 which is not 0. It's to work modulo discontinuities. Either you work modulo discontinuities everywhere, or you work modulo discontinuities everywhere but in the first entry. That's here. That's a very important point. Yes?
So this is for the even ones, but are there other types of recurring relations?
The odd ones have no problem. Assuming all standard consonantality conjectures, okay? The odd ones are not supposed to be proportional, so zeta 3 is not proportional to pi cubed, as far as we know.
So how using Brown definition, the third term is killed there, the term that we don't want?
You have to throw away all. Another way of achieving this is to say that you always have to put to 0 pi except in the first slot. Because you work modulo discontinuities but in the first slot. So if you do that, then put to 0 all the zetas that's in the certain slot. So you just get zeta 4 tensor 1, which is precisely that. Okay? Which is the same as what I would have gotten here by throwing away the zeta in the second slot.
I forgot that also that side was modified.
Yeah, everything is modified. So, the more correct way of saying things is what forms a Hopf algebra. It's actually not the polylogs, it's the polylogs modulo Branchplatz in some sense. Yes?
So are you saying the 1 and 2 are completely equivalent?
No. No. They're not equivalent. This means you consider all polylogs modulo der Branchplatz. That means you keep branch cut information in the first slot, but only in the first, not in the second.
Okay, but then shouldn't you always choose the second one because it stores more information?
That's what we will do in practice.
Ah, okay.
Okay, I'm just saying those are two ways of thinking about it. Those who want to learn later on, not hear these lectures about cosmic algebra, that would be the Rahm periods, that would be motivic periods. Yes?
So the definition of the coproduct, I guess you make it in that way such that it satisfies the right property, but then you seem to show that it doesn't satisfy the correct properties. So I guess that in the original proof you were not careful about the branch cut, or
What? The original proof, this lead that I wrote is defined modulo its branch cuts. The proof that I get a Hopf algebra only goes through if I define my polylogs modulo branch cuts.
and that's why then you need to.
Yeah, then Francis Braun in some sense has shown how to correct that and to put in that these steps. Okay? More questions? This is a very important point. It's probably the most subtle thing in the whole construction.
Can you repeat the argument of the 2 pi I? Just a little bit.
Yeah, I'm just saying, so this, do we agree that this implies that?
Okay, because it's square.
Because delta is linear with respect to, well, if you want, of pi squared over 6, that is, well, now I need to mark it in my head, 1 over 6 minus 1 over 4, 2 pi I squared, and so on, right? So the second one implies the first. The second one here becomes stronger. That covers all the cases, but it shows you what the special is in some sense not zeta 2 is, what the special is 2 pi I. That's the residue. That's what character. Everything is in some proportion to pi I comes from taking a residue, roughly speaking. So that is discontinuity contribution.
So Sorry, ask again. So
Yeah.
for function, we use that coproduct there.
Yes.
For example, when we encounter constant function, we use
So it means
that.
let me maybe let's go through the examples and then it's
Okay.
very clear.
Okay.
In practice, it means throw away pi except in first entry. And this is cooking version. Throwing away pi is equivalent for polynomials to say that you work modulo discontinuities. Okay? I guess this we can agree. Because every discontinuity is proportional to 2 pi I. If you throw away all 2 pi i's, you throw away all discontinuities.
Yes.
Sorry, is it then a conjecture that this is a Hopf algebra?
No, it's actually a co-modulo.
Okay.
But it's a Hopf algebra. I didn't want to go into distinction, but it's a Hopf algebra. It's Polynomials modulo der branch cuts. If you put I pi, you get a comodulo. But the distinction here for the lecture is material. But it's technically a comodulo and not a Hopf algebra.
Sorry, maybe I missed it. But, so delta is linear with respect to what?
Rational numbers.
Rational numbers.
Or even algebraic numbers if you want. That doesn't matter. In all of these worlds, algebraic and rational, you can interchange it freely, roughly. Yes?
Suppose we're working different functional bases, such as this, they don't have a branch out that's like the single value or.
Very good. So, that's a very good comment. That's now only for those who know what single value polynomials are.
Maybe you can repeat the question, I'm not sure.
So, the question was, imagine you work with single valued versions of polynomials. Now, for single valued versions of polynomials, there is no branch cut in the first place. You can also say that indeed the single valued versions of the polynomials, they do form this general Hopf algebra. Because then 2 pi I is not there in the first place, and they form a general Hopf algebra. Another way of doing exactly the same algebra than what I'm going to do is to say that in the first slot, they have the polylog, and in the second slot, they have the single valued polylog that corresponds to. So if there are a log in the second slot, I could also write down the formula where I put the single valued log in the second slot. That would have the same effect as this. So that those are two equivalent ways of representing the same mathematics. Okay? The reason I prefer to do it this way is, well, A, historical, because that was there before the single valued polynomials were generally introduced. B, if you do the single valued version, then you have to carry along all the homomorphic stuff, which is harder to deal with. The algebra is the same anyhow. So it's easier to say, I work with the holomorphic functions, and in my head I always scratch all 2 pi i's. But you're right, I could also, instead of saying I work with polynomials modulo der branch cuts, I work with single valued polynomials. Okay? Good. So what can I do with this? So, since the clock is ticking, let's take a simple example to illustrate all the points. Let's first take a trivial example and then take an example that is slightly less trivial. So, imagine I give you the following object. Just say you compute the loop integral and that's what comes out. will handle it. And let me act with the co-product. And what I'm going to do is, I'm going to use a notation, which is actually very natural. Find it here. So I'm going to use a notation that says just this factor, I will call it delta n minus k. What I mean by that is, you see that every slot here has a specific weight. And when I say delta sub some numbers, I mean I take out only the terms that have, say, weight n minus k in the first slot, weight k in the second slot. Okay? So let me compute, let me call this t. Delta 1, 1 of t. This is delta 1, 1 of d2 of z plus delta 1, 1 log z log 1 of z. Now delta 1, 1, if you look, it's gone. It looks like this. We had it just before, we wrote down what delta v2 is. That is, we get out of here. We had before a formula for delta v2, that 1 tensor 2 plus the 2 tensor 1 plus that term. And this is a product. I know how to compute a co-product of a product. And since time is short, let me just give you the result. This shouldn't surprise you too much. I just get the product is commutative, so I just get the significance. So what you see now is, of course, that term counts as that term. And you get log z tensor log 1 minus z. But what is that? That is the same as what I had here, except that z and 1 minus z. Yes?
I think there is a typo. The first line you have the line 1 minus z. The second line
yes.
the line
Sorry.
z.
Yeah,
And, let's leave it like this probably. Yes, exactly.
Yeah, then I need to put a minus on here probably. No, it's fine. Yes, let's do it like this. So I get this, which is the same as what I had here, except with z and 1 minus z swapped. Right? And we change the sign. So this came actually, it's the same as delta 1, 1 of minus c2 of 1 minus z. Okay? So by acting with delta 1, 1, I've revealed that that combination has the same image, the same co-product as a single term. So what do I conclude from that? Let's just write that here. From that I conclude that t is actually minus v2 of 1 minus z, well, plus something. This something must be, well, it's an object that, well, lies in the kernel of delta 1, 1. And I told you there are no relations among objects of different weights, so it must have weight 2. It also better be a constant, because otherwise I would have detected it with delta 1, 1. So the only thing it can possibly be is something proportional to pi squared. Some constant of weight 2. Because that is something that I don't decompose. just goes to itself tensor 1. So that means that delta 1, 1 of zeta 2 or pi squared is 0. Delta 1, 1 would have weight 1 in each slot. What is C tilde? Well, C tilde I cannot get from Fourier derived considerations. That is like an integration constant. But I can recover it, just like an integration constant, by looking at a specific point. For example, when z is equal to 1, you see from up there that t is V2 of 1 plus 0. Because log 1 goes to 0 faster than log 1 minus z diverges. Z goes to 1. From the second line, I get that this is minus V2 of 0 plus C tilde pi squared. So, if you compare this, you find that C tilde is actually 1 over 6. This is pi squared over 6. Zeta 2. So I found that T is actually minus V2 1 minus Z plus pi squared over 6. Which is indeed the relation that I wrote down this morning at the first lecture. So even if you didn't know that relation, you discover it just by purely algebraic consideration in the subart. Just follows the Hofmann structure. No, they have not done any integral manipulations. Of course, I can find the same relation by integral manipulations, but I don't have to. You say, well, then it's overkill, because why do you need this whole machinery if you can do the same as integral manipulations? That's correct. Here it's easy. That's why Euler did it 200-300 years ago. But if you had to do the same, where T was not this, but it was 17 pages of multiple Goldilocks of weight 2 in 3 variables, it's a different story. Okay? Shall we look at another example? So the upshot is, this gives you practice. This gives you a handle on dealing with polynomial expressions. You get way too much out of it, a way to analyze them, a way to derive identities. You have ways to derive identities. You can check if things are linearly independent, and it's purely combinatorial. There's no integral manipulations involved. Let's look at another example. So let's take, so what about things like Ln of 1 over x? Can I somehow relate that to Ln of x? Well, let's proceed step by step. First n equals 1. And just to be concrete, let me say x lies between 0 and 1, and I decide the physicist way that x is a small imaginary part. So that I know what log. So this is just the physicist's way of saying that log minus x for x between 0 and 1 is log x minus I prime. Saying that x is x plus a0 and it's log minus x is log x minus f5 is exactly the same. Just saying on which side of the blank are they. Okay, well, what happens if I have n equals 1? d1 is 1 over x. And that is minus log 1 minus 1 over x. Here it's a log, it's easy, you don't have to do much. This gives me minus log 1 minus x plus log of minus x Okay? I decided that my fixed all my branch paths such that log minus x is this. Okay? That was easy. It was easy because it was a log. What about n equals 2? Oh. So what can I do for E2 over 1 over x? So what would you do? In applications, what would happen is you have E2 of 1 over x between 0 and 1. D2 has a branch cut from 1 to infinity. Actually, every dn has a branch cut that goes from 1 to infinity, just like here. Right? You see that you get the log of negative argument. So that function is essentially, if you want, well, ill-defined in the sense that you would like to make all the imaginary parts explicit. How could you proceed? Well, you don't know what to do with D2, so turn it into something simpler. Turn it into things of weight 1. Instead of having one object of weight 2, turn it into 2 objects of weight 1. We said up there what delta 1 of D2 is, so that is minus log of 1 minus 1 over x. Tensor log x. Tensor log 1 over x. Okay. But those guys I don't know how to handle. The first guy is precisely the one I had here. So this is minus log 1 minus x plus log x minus L pi. The second guy is just minus log 1 over x, minus log x. Right? Log 1 over x. Now, let me expand this out. I get log 1 minus x, tensor log x. That's that one and that one. Minus log x, tensor log x. Minus, plus I pi tensor log x.
Maybe the signs are the other way around.
Minus, excuse me, plus. There's a minus here. The D2 is minus something.
Minus in the round bracket, the third minus in the second.
Minus gives me plus, plus with a minus. So minus gives me minus here. No, that cannot be.
It's all exchanged.
Where is the exchange?
Next one also, the last one.
Yeah.
The first bracket is not logarithm 1 minus x, it's minus logarithm.
Sorry, where?
Remove 1 minus and should be okay.
Okay. Like that? You say? Minus is minus.
No. The big minus should be removed. The whole is minus.
That one?
Yeah.
Oh, okay, yes, you're right, yes. And also my signs look better. Minus, plus, that's yes, what I want. Plus, minus, plus. Okay? Sorry. So, well, I guess you see the first one. That is delta 1 of minus E2 of x. Right? The second one, well, you have to check it, but I think it's not too hard to see. It's minus 1/2 log square x. You see it up there, we said that the product gives me the symmetric combination. So if I add a square, it gives me twice the thing cancels with itself. So log x comes from 1/2 log square x. And the last one is subtle, because you see, it's quite asymmetric. Pi is in the first, but not in the second. Nonetheless, due to the special way pi works, this comes from I pi log x. And here you see why pi is really so special. It only works because pi only sits in the first slot. Pi was also in the second slot, it didn't work. Okay, so from this you conclude that v2 of 1 over x is now minus v2 of x minus 1/2 log square x plus I pi log x plus some constant of way 2, which vanishes under delta 1,1, so it's proportional to pi squared. Let's look at a special point at x equals 1. It gives me here v2 of 1, so zeta 2, equals minus v2 of 1 minus zeta 2. This is 0, this is 0, plus c tilde pi squared. And this implies that c tilde is 1 over 3. So you found the relation between v2 of 1 over x and v2 of x without even knowing what the data is. The only thing you need is the co-product. You wouldn't even need to know the representation of the function. In that sense, it's purely combinatorial. Again, this is an identity that was known a long time ago already to Euler, but now imagine that you do this for g, a, b, c, x. The combinatorial way would be exactly the same. The integral way would be very tough. Questions? You could now go on and you could do Lie 3. For Lie 3, you would have a term where you have v2 of 1 over x in the first slot. You would insert the function in the relation you just found, and you would recursively go through until, well, you would find Lie 3, and you would get Lie 4, you would need Lie 3 of 1 over x, Lie 2 of 1 over x, which you already know, and so on and so forth.
It's quite related to what we said quite before. So we found a way to basically find identities to reduce our basis.
Yes.
But how do we know that our basis is actually enough to sum the whole space? I mean, if we don't need more.
So that is now, okay, we'll come to that very end. So that is then the question of what do you start from, okay? You don't know, you never know. That is, you need some magical wand that tells you for your 7-point MHV armed ends for super animals, that is the maximal class of functions. We'll see in a second a little bit about that. So this is really just about relations among functions and how to resolve them. Okay, so we have like 20 minutes left.
Five.
Yeah, let's say that's 5 minutes for questions. So, before we go on with the last topic, 2 small comments. We just following. So, we have these 2 slots, and they were quite asymmetric. You can ask, is there another meaning to these 2 slots? So what is the meaning of the first slot and what is the meaning of the second slot? What do they encode? What kind of information do they encode? So, let me first ask another question. I give you a polylog. What are the kind of natural operations you can do on a polylog? One thing is multi-valued function, compute its discontinuity across some cut, right? I just give you a polylog, I don't give you anything else. And you have to waste some time, so what can you do with it? Well, maybe you can go and check what is this discontinuity across some of these branch cuts. The other thing you can do with it is, well, that thing was defined as an integral. You can go and kill an integral by computing the derivative. That's probably the only two natural operations you have. Now here you have two slots, the left and the right. You have two operations. It's precisely these two operations that are encoded in these two slots. So I said there's a whole there's a combinatorial way of doing things. And the combinatorics that is encoded in these two slots is just the combinatorics of taking discontinuities, taking derivatives. Because that's the two operations that you have when you have an integral. And let's first look at the following. So you have v2 of x. This morning we defined it like this. From this, I guess you agree that d over dx for v2 of x is minus log 1 minus x 1 over x. Okay? Now let's look at delta v2 of x. Let me write it down. And let's go and let's only take the derivative in the second slot. So if I take the derivative in the second slot, then here I get 1 cancel. The derivative in the second slot is log, well, derivative of a function, so x divided by x. The next one, the derivative in the second slot gives me 0, because the derivative of 1 is 0. And here I get minus log 1 minus x, hence the derivative in the second slot is 1 over x. And we said that, well, the arguments here, we discussed this in the previous hour, should be algebraic numbers. Like we looked at polynomials evaluated and algebraic numbers. X is an algebraic number. But everything is linear with respect to algebraic numbers or rational numbers. So 1 over x is a rational number, so that I can pull out. The same here. So that sits, if you want, outside. And also the minus sign can pull out. And that, oh sorry, I did the other, so 1 minus x. And that is indeed delta log 1 minus x. So what you find is that computing the co-product and then taking the derivative in the second slot is the same as if I had only computed, we had first computed the derivative and then computed the co-product. With that, minus 1 over x delta log 1 minus x is the co-product of the right hand side. We can summarize this by, let's put that in red. I use 2 colors because there will be this continuity part as well. Delta of the derivative is the same as the derivative only acting in the second slot. I gave you an example, you can prove that in general. So the second slot encodes all the derivatives of the function. And here, well, add one variable and it's called d with the x to be any derivative in the variables. It always works. So what about the other operation, the discontinuity? Well, discontinuity, so exactly the discontinuity of E2 is, so E2, we said it many times, has a branch cut starting from 1. So let's look at the discontinuity across this cut. And the discontinuity is here we go. The discontinuity of V2 of x across this cut is 2 pi I, or minus 2 pi I, depending on which way across the cut, times log x. Now, let's compare to this formula. Now, use another color. Now, let's only take the discontinuity in the first entry. So the first entry here, discontinuity of 1 is 0. Discontinuity of that guy, well, we said is 2 pi I log x. Tensor 1. Here, minus discontinuity of log 1 minus x is, well, if you do it consistently, this gives you minus 2 pi I, this convention shows there. Because you see this is minus x, so this goes in the other direction as x. Tensor log x. So this gives you 2 pi I log x tensor 1 plus 2 pi I tensor log x. And again, due to the special role played by 2 pi I, this is actually delta of 2 pi I log x. Which is precisely the discontinuity, the co-product of that side. That is, if you want, a deep reason why 2 pi I has a special role in the first slot, because discontinuity, this first slot is the one that knows about the discontinuities. Okay? So the one that gives you meaning to the two entries in the co-product. It's discontinuities and derivatives. Questions? Yes?
So when we define the co-product as the way Nelson Brown did, we only list the constant proportional to p squared, right?
Yeah, yes.
Right. And if you did it the way Goncharov did, what would you use?
Well, again, Goncharov defined things modulo branch cuts, okay? Modulo branch cuts, that is the correct answer.
Okay.
Now, that can be made more concrete. It's what your colleague asked before. There's some single-valued version of the dialog, so the Bovigna dialog, which, well, actually, yeah, Bovigna dialog has even would satisfy that. There's a single-valued version of the dialog, which is close to the dialog, which indeed satisfies this function equation.
So if you go to higher weights, there will still be only missing the constants, right?
You're only missing the constant, yeah. Now, empirically, these constants are always zeta values. But I don't think that that's a proven statement.
So is there, I mean, to prove this relation, we basically have one expression, second expression, give delta 1, 1 to both and so that they're equivalent.
Here I derived the expression, right?
Yeah.
Yeah, I did not say the two and one is the other and they say the same. Here I'm really discovering this relation up to this pi squared.
Yeah, so basically my question is how to get from that delta 1, 1 value back to what original expression.
Here?
Yeah, so from...
Well, I know that the delta 1, 1 of this guy is that, which is the same delta 1, 1 as the one that I have here.
Yeah, okay. Yeah, right. So to know this, you've computed that delta 1, 1.
Yes.
So in general, do you need to compute delta 1, 1 from the whole basis to...
Yes, yeah. The way you would do it is that, so you have a bunch of functions. You could use this to figure out which ones are linearly dependent. Yeah? Once you can do that by saying, I write down a Gaussian linear combination, and I require that they remain linear dependent after I make them simpler and simpler and simpler.
And is there a way to do this reconstruction without computing delta 1, 1, 1, 1 from the whole basis? Because the whole basis...
Not in general. Not in general.
I mean, the basis grows exponentially, right? With weight.
The basis grows very quickly, yes, but there's no way to do that without having a basis. Because, I mean, it's a point in the vector space, right? Whatever, I mean, there's another way, this is now a bit provocative, of saying, what is the correct answer? It's that equals itself. I found, if I declare that d2 of 1 over x is basis vector, I found the decomposition. d2 of 1 over x equals d2 of 1 over x is coefficient 1, and all the other basis elements have coefficient 0. So I have to make a choice. What I call my basis. For example, here my basis, why do I not like d2 of 1 over x in my basis? Is because I declared x to lie between 0 and 1. And I want my basis vectors, for example, to be real in that range. So I make a choice. That is why I like d2 of x better. But it's a personal choice.
The only question is that performance. If you need to...
Performance is an issue, yeah. But it's always a question of if something is slow but you get it done, or not knowing how to do it, then I prefer slow and getting it done. Also know that the things that we want to compute in practice is 2 loop, 3 loop, low weight.
Not everyone.
Not everyone, but that's where actually bottleneck exists, say, from the practical point of view. You want to do computation, but you see the bottleneck is the 2 loops. All right. Okay. So we have 5-10 minutes. So very last topic. It's more like a comment because we'll follow some what I've said. I think it's important to comment on it because that's something you often talk, so read the papers, it's called symbols. So from what I've said, symbols are very easy to follow immediately. So we have now a co-product that allows us to take a polylog of weight n and to decompose into pairs of simpler objects. We also said in the hot part of everything is called associative, so I can iterate this procedure and break it into simpler and simpler pieces. So I can start with something, say, that has weight 3. I get something that has weight 0 and weight 3, that is 1 tensor weight 3. I always use 2 trivial pieces, remember the ones that have the 1 and weight 0. Then I would have terms that have weight 2 and weight 1, and terms that have weight 1 and weight 2. Let's forget about those guys for now, because you see they carry no new information, it's just a copy of that guy. So now I could go and break this guy into 1, 1, and 1, and this guy into 1, 1, 1. Right? Co-associativity tells me that that is the same. Whatever way I do the breaking apart, I get the same answer. So that tells me that for every MPL of weight n, there is a unique way decomposing it into an n-fold tensor of objects of weight 1, meaning local items. That object is called the symbol. It's like, if you want the crudest approximation to your function you can make, you break it apart into lots of logarithms. For example, the symbol, and let's call that S, symbol of V2 of X would be, well, we've written that many times, that is precisely that guy. The symbol of V3 of X, you have to go to the algebra and see why? Because if you remember delta of Dn, or E3, of X that contains one tensor E3 plus V3 tensor 1 plus V2 of X tensor log X plus V1 of X tensor log squared X of V2. So take, for example, this guy. This would be 2, 1, weight 2, weight 1. And now you break the 2. You plug in this, so you see here, there you see delete 2 tensor log. This is V2 tensor log. Or you see Li1. Li1, remember, is minus log 1 minus X. This is this term. Tensor log X, which comes from 1/2 log square X. So the symbol is the maximum way of breaking things apart. Conventionally, you see, everything is log now. So this is usually then written minus 1 minus X tensor X. You just drop all the log signs because they're kind of redundant. But it's always understood that this means log 1 minus X tensor log X. This would be minus this, and so on. So when people talk about symbols, that's what it is. It's just the maximum decomposition of these functions. The very last thing, because you often see people write things like this. They say, if you work with symbols, then if somewhere in the symbol you have a product that becomes the sum of the symbols, yes, of course, because it is log X times Y equals log X plus log Y. Okay? There's all these secretly log signs everywhere. people say things like, whenever you have 1 inside of a symbol, you can throw it away. Yes, because it's actually log 1, which is 0. You see things like, also -1 you can throw away. Yes, because log -1 is I pi, and you said that I pi's we throw away except in the first slot. Okay? So when you hear people talk about symbols, it's just the crudest approximation to the some modular structure that you can have. It's very convenient because you see the calculation of rules are very simple. Because you're just computing these logs. But it's also, you lose a lot of information. For example, now the symbol of zeta n is 0 for all n. Why? Because we said the co-product of zeta n is 1 tensor zeta n plus zeta n tensor 1. There's no thing that has a log anywhere. So I cannot iterate this thing. So the more you decompose an object, the more information you lose. But the simpler the calculations become. So here's the trade-off. And maybe the very last thing, the comment that was before, how do I know what is my space, what do I start from? This is what people often call the alphabet. It's basically saying what are the arguments of the logs. So after I decompose the function to a maximum, what are the arguments of the logs that I could possibly have? That's then like the imprint of the space of functions. If I tell you that the space of functions has the property that if you compute a symbol, those are the only arguments of the log, these are the arguments of the logs that show up, you have in principle defined the space of functions. I'm doing this operation when it works. It can be hard to construct a space of functions, but the principal function space is well defined. And that is what people do when they bootstrap unprecedented equals 4. We have ways to guess what we believe is the arguments of the logs that show up, or the entries in the symbol. And from that they build the space of functions. They use the software structure to state that everything is linear independent, to build an ansatz. You write down the answers and then you match it to some physical constraints to fix the coefficients. That's roughly what happens. Do we have a better way of explaining it? I think in broad terms that's what it is. Right?
Absolutely. You yourself have also contributed.
Yeah, that's a long time ago. Things have evolved a lot since I worked on that. Okay? So I think this is then the right time to stop unless you have questions. I have unfortunately to leave in half an hour, so if you have questions, it must be now or
never.
Not a kind of problem, but how do you get this continuity in the dialogue?
Sorry, can you speak up?
Yeah, this is something I should probably know, but how do you get this continuity in the equation behind log n?
Can you repeat the question and what's the right?
Sorry?
Just repeat the question and
Yes.
what's the right?
So the question is, where did this come from? Well, you have to really look at, okay, I'm now giving a very hand-wavy reason for that. So, you have a branch, so here you have two singularities in principle, it's 0 and at 1. Okay? In the integral. We said in the very first lecture that discontinuities, really think of them as residues. So what is the residue at t equals 0? Oh, sorry, this is t, of course. At t equals 0, it would be log of 1 minus 0, which is 0. So there's no residue, so there's no discontinuity when I turn around 0. So that's only discontinuity around 1. So that's why I have only branch cut here. Okay, that comes from the discontinuity of the log. Now, we become very hand-wavy. The discontinuity of this log, we use it here, is minus 2 pi I. So, the discontinuity, when I cross the cut, gives me minus integral from 0 to x dt over t minus 2 pi I. Okay? So I get plus 2 pi I times the integral dt over t, which is a log. I say it's very hand-wavy because like this would diverge, but it shows you why this 2 pi I times log. It's because there's this log in the integrand, which gives you 2 pi I, and then one integration left, which gives you a log. If you do it rigorously, not hand wavingly, then you see that there's 1 down here. If you do it rigorously, because that is where the branch point is. But the structure 2 pi I times log from the vectors. Yeah?
Can you repeat once more? How do you reconstruct this constant and how do you know it's a constant?
So, constant is reconstructed by looking at the special value. Or like,
I know,
integration.
but how do you know what weight it is and how do you know?
So the weight I know because we said there are no relations.
You answer the question.
It's okay, they misunderstood the 530, I think.
So the weight of the constant you know because we said there are no relations who count in different ways. So whatever constant it is, if I have weight 2, it must be weight 2.
But when
because you wrote down something that had weight 2 when you started, you write something else which was also had weight 2. There cannot be weight 3 p's in that relation altogether.
okay, so it's
Why constant? Because this you have to check what this whole problem does. Whenever there is a polynomial that has a function dependence, the co-product will act non-trivial on it.
yeah, so independent path functions should only
You know that the integration constant is a constant. It is actually literally integration constant. If you translate everything back to the integral definition, it is the choice of the point where you start integration. It is literally an integration constant. But you can also do it combinatorially by knowing that whatever polynomial in X you would write down, the co-product would act non-trivially on it. Non-trivially in the sense of you would have detected it before. So the only thing that is left at that point is the constant. It's a hand-wavy argument, but I mean, if that thing was, say, E2 of 1 minus x, you could easily check that delta 1, 1 would do something to it that you would have seen it before. Because it must be something that lies in the kernel of one of the things that you had before.
Sorry, could I ask you again the question on the discontinuity? Because you said we have to treat that as a residue.
Yeah.
But then when I take a residue, usually I send like x to 1, and then we have any dependence on x.
That is a double integral. You would need to write this double integral, swap the two integrals around so that you have 1 over 1 minus x times something, and then take the residue.
Okay.
And this is actually, so, you would need to write this as an integral from 0 to x. Well, let's do it in detail. I can write it's just fucking algebra. Okay? Those guys I know. They are logs. I know how to take compute discontinuity. How do you compute the discontinuity of that guy? Well, that is dt over t minus 1, 0 log x. And now the residue at 1 will vanish. But you have the contribution from here. This guy has no discontinuity at x equals 1. This guy has, which is 2 pi I minus, then you get log x. Find the same answer as what I had given you before. And this computed log is again the residue itself, right?
Okay. No, I understand because I have 2 variables and
You have 2 integrations. Yeah.
More questions? I mean, Marie's gone at the moment, so.
So if we say that the conjecture that you said about the direction is wrong, say.
No, it's wrong.
No, I mean, like, assuming
yeah.
this is wrong, how much of this analysis?
Okay, repeat the question, please, because
So the question was, imagine that the weight didn't provide a grading, so that was wrong. I think then the question would first bounce back to mathematics, because then many buildings in math would crumble. And yeah, then these are conjectures, yes, but I don't think these are conjectures that any mathematician would doubt. Of course, they are not proven. But if they are wrong, then we first go back to math and we have to ask the mathematicians, okay, since these conjectures were wrong, what do we put up instead?
Okay.
Again, for the benefit of the students, do you have a reference for the things that you presented today? I don't think we saw any in the...
Yes, so there's a writer of this from Tarzi 2014, where most of these ideas are collected, and also in there you find, I guess, most references, like the original stuff. And this is probably the place where everything is condensed in a pedagogical manner. And there you can then trace back the references if you want.
Very good. Before you with another question, let's first thank Claude again.